University Arms upstairs seating area for later on, so puts it from 5 o'clock. Said there might be sort of 20-25 of us, so everyone can come obviously, and see you all there. Right, I apologise to anyone that's seen me give a talk before. It's going to be largely the same with a bit more background. I'm trying to get to the point where I've got a nice 40-minute talk that I can give forever for the rest of my career. So I'm already planning for that late stage.
So no changes in the next 30 years then, in terms of like...
The research career is over, yeah?
So yeah, obviously, for anyone that doesn't know me, I'm Lewis. So the bulk of everything I do is working on separate plutonium waste forms. And there's not been much variation so far in my career. I've kind of landed on my feet with everything in terms of every time I've taken the work forward, there's been loads of fun. I won't go into too much detail on UK's civil nuclear infrastructure, but for those who aren't aware, obviously the UK has quite a complex legacy of radioactive waste, with the first sort of fission experiments beginning in 1966. Nuclear power contributes, well, on average, it's difficult to find correct figures, but generally between 15 and 16% of the national electricity supply. Again, probably not a surprise to anyone, we've operated 3 types of reactor, not including nuclear reactors, and these are Magnox, AGRs, and PWRs. On the left-hand side, you see there's several nuclear sites. These cover reprocessing, reactors, R&D, defence sites, fuel and fabrication sites, and enrichment sites, medical, industrial, and then waste disposal as well. So spent fuel historically has been reprocessed at the Sellafield site. As Paul said, that process is largely finished now. Highland waste product is vitrified on site and is stored away in final disposal. If anyone's been following the news with the GDF recently, things are looking a bit sketchy. It's a shame Neil couldn't join us because it'd be good to ask his brains, pick his brains maybe in the pub when he's not on microphone as to what he thinks the current status quo is. But from what I gather, there's a lot of pushback at the moment with respect to cost, and people are generally worried that this volunteer approach to siting the GDF might not be going too well. So I suppose in the next few years we'll kind of see how that goes. If one of the community partnerships gets taken forward next and they eventually vote no on a test of public support, who knows where that leaves the future of the UK. Maybe we just drill a bunch of boreholes and be done with it. Let's see. But importantly, as part of this complex waste inventory, the UK has a substantial stockpile of plutonium. Aidan covered that earlier, and it's the largest non-military inventory held anywhere worldwide that we know. Okay, so how does plutonium form? In brief, there are sort of 2 main processes that happen inside the nuclear reactor. You have U-235 undergoing fission when contacted with thermal neutrons, generating light fission products, so xenon or lantanides, iodine, cesium, technetium, all the things that are an absolute nightmare in the environment that we need to obviously isolate, and we do that via vitrification to a plasma. Other processes that happen are neutron capture. So the U-238 matrix is, with respect to energy generation, is largely inert. It's mainly just a matrix to contain the U-235. However, what we do find is that the U-238 will absorb neutrons. This results in the formation of higher actinides. So U-238 absorbs a neutron, becomes U-239. That's metastable for quite a short period of time. It undergoes beta decay, forms Neptunium-239. After a couple of days and some more beta decay, that forms plutonium-239. In Magnox's conversion ratio is about 1,235 atom per uranium-235 atom. In PWR's, the conversion ratio is lower. That's because water is a more efficient moderator than graphite. So when you put this all together, what you understand is that further isotopes of plutonium and then the minor actinides form basically as a function of time, and as well as other things, reactor geometry, initial burnup conditions, enrichment, etc., etc. But generally, the longer you leave your fuel soaking in neutrons, the more plutonium you're going to generate, and the later plutonium isotopes you're going to generate. So as a starting point, if you want to generate material for a weapons program, if you want to procure weapons-grade plutonium, you want a really high yield of plutonium-239. So in order to do that, you want quite a low burnup. So if you can see down the third line down, the mean fuel burnup, gigawatt days per ton of heavy metal, you've got quite a low burnup for defence material. this is because you want, again, high isotopic purity of 239, or as high as you can get, but ideally as low 240 as you can get. So 240 has spontaneous fission. So basically, if you've got quite a high yield of this in your weapons material, you get what's called a fizzle bomb, as it's sometimes called. But burnup is basically a controlling factor in selective yield, which is a particularly important isotope, which we'll come on to in a bit more detail, is plutonium-241. This is because it's got quite a short half-life and results in americium-241 in Earth, which can become a problem with respect to plutonium storage over long timescales, which the UK unfortunately has found itself in. So anyone that's done Math 3.910 will realise I've just plagiarised these slides directly from Neil Hyatt, so I'll sort of whiz through this, but a brief history of how plutonium has been produced. So in the 50s through to the 60s, plutonium was first separated. Again, it's no secret that the initial purpose and the initial motivation was procuring an independent nuclear deterrent. The US had one, Russia had one, we wanted one. So the first separation was achieved in 1951, and the first test was in 1952, which was called Operation Hurricane. In the 60s, there was assumed to be limited fossil fuel reserves. Uranium reserves weren't thought to be as vast, so there was basically a big motivation for a closed fuel cycle, which is to say fuel would be reprocessed, uranium and plutonium would be separated out with the view to generate either fresh fuel, MOX, or in the case of plutonium, obviously, material for the weapons program. Gen 1 reactors, Magnox, used natural uranium metal. There was a series of test reactors, fast reactors up at Duma. The idea these would recycle reactor-grade plutonium. Gen 2 AGR reactors start to enrich the uranium and use UO2 fuel, and obviously the Gen 3 PWR with slightly higher enrichment. Okay, so Magnox was reprocessed at B205, starting in the 70s through to the 90s, and AGR fuel was reprocessed at Thorpe, thermal reprocessing plant. Prototype fast reactor fuel was reprocessed at Duma, and then in the 90s everything kind of changed. So there was an idea for a full fast reactor fleet in the UK to use all this plutonium that we were no longer going to use for a weapons program. That was abandoned for various reasons. There was new reserves of fossil fuels were discovered, particularly in the North Sea. There was increased, presumably due to better technology, we were able to basically understand that there was more uranium than was thought, and energy prices at that time, it seems, were sort of a bit lower and a bit more stable. So with that, and for various other reasons, commercial not least, there was an absence of a route to consume this plutonium, despite the fact that we were still reprocessing it. So we were basically generating a lot of plutonium, separating it, with no long-term strategy for managing it. So in 2004, the NDA was established. So pre-2004, I'm not an expert, I'm not sure what it was. Obviously there was BNFL, but in terms of a government-driven arm of waste management,
NIREX, there's quite a few different, yeah.
The NIREX didn't have any high-level waste
No,
responsibility.
no, good question.
So anyway, as part of the Energy Act in 2004, there was a requirement to develop a long-term management strategy for plutonium. Okay, so how is plutonium purified? So obviously in the reprocessing stage, you're converting spent nuclear fuel, obviously, you're dissolving it in nitric acid, you're oxidizing uranium to uranium-6 and Plu to Plu-4 in solution, and then you basically need to separate those out. So Plu is reduced down to plutonium-3, separated from the uranium, and it's conditioned by addition of hydrogen peroxide at about 60 degrees to Plu-4 nitrate. This can then be precipitated by oxide precipitation, converted to plutonium oxide by calcining, and then packaged for storage. So the properties of Magnox and Thorpe plutonium are different, and they're largely blended. They're in a process called rainbowing. So basically, some of these packages contain varying proportions of Magnox and Thorpe plutonium. If anyone ever gets the chance to visit Central Laboratory at NNL and see the experiments they're doing there, what they're doing is taking some of these legacy packages and they're basically cutting them open in these big glove boxes and tipping out the canisters into these big trays. So what you can see here is plutonium oxide. At least for the longest time, I always assumed it was a black powder. But it's not actually. It comes in a range of colours, but it seems that most plutonium oxide is actually kind of a dirty green kind of tan colour. And for context, this box is about that big.
It's about 7 kilos of pollutant
so
there, pollutant oxide.
Many kilograms at a time. So when you see the scale they're working on, and obviously they've got to work through tons that need repackaging. This is obviously a huge operation.
You don't want to trip with that down the stairs.
Yeah. So when we were there last, what they had is they had one of these inside one of the calcination furnaces. So what they need to understand is, in the previous 60 years of storage, long-term storage, how have the chemical and physical properties of this material changed? What comes off? Obviously, the analysis they can do is fairly limited, so they're stuck to things like TGAMS and things like that. But that's a substantial bit of work, and I'm not too familiar with the details of how that's going, but at the minute they're basically building a new plutonium store. They're repackaging a lot of this material until such a time where they can mobilise. Okay, so what are some of the difficulties with long-term storage? So there are multiple, not least economic and political drivers for getting rid of it sooner. We'll come on to that in a sec. But physically, there are two processes that make storage more difficult with time. The first one is chlorine. So historically, when we first produced this material, it wasn't envisaged that it would stay in storage for 60 years, 70 years. So not that the design requirements at the time weren't suitable, but they didn't think that they had to leave these PVC-lined stainless steel canisters there for such a long period of time. And what's happened is some of the packages, at least, have undergone quite severe degradation. Chlorine content is difficult to estimate. If you read this paper by Webb et al. From 2019, it's estimated between 2,000 and 5,000 ppm. And they've estimated that this is equivalent of basically 1 microgram of chlorine per gram of plutonium dioxide, which doesn't seem like a lot. And I'm not an expert in chlorine chemistry, however, it does seem that any amount of chlorine can cause real problems with respect to corrosion. And obviously, you don't want to be generating chlorine gas, you don't want to be generating things like oxychlorides, some of which can be quite explosive. And most importantly, you can't use chlorine-contaminated material to make fuel. So that's one of the drivers as to why the immobilisation route has been chosen. We'll come on to that in a sec. The other one is americium ingrowth. So I mentioned earlier that plutonium-241 decays by beta to form americium. The half-life of americium is about 433 years, and then it forms neptunium-237. That basically ends the decay chain because the half-life of Nep-237 is like 2 million years, very long time. But importantly, about 36% yield, americium-241 will kick out sub gamma. Obviously, this is highly penetrating, imposes, it's got practical significance basically for long-term handling and storage, increased dose uptake to workers, and obviously the longer you leave it there, the worse this problem gets. Because although 433 years half-life is not a huge amount of time, in the context of like a storage program of 50 to 100 years, it is bad and it's only going to get worse. So this is two reasons why we really need to understand chlorine and americium absorption onto blue oxide. The difficulty is, even in a lab setting, simulating hydrogen chloride absorption onto powders is not only dangerous, it's difficult, and also working with americium is extremely difficult. So in both situations there needs to be quite clever surrogate chemistry, and Charlie and Alex will be the guinea pigs for figuring out how on earth we do this, which is quite exciting. Okay, so timeline of key policy milestones. So there were there were more documents than this, and there are many public consultation or feedback documents that you can find. But the main pieces of literature, at least as far as I can find, are these 8. So as far back as 1997, the Royal Society was publishing independent reports raising what was the phrase that you used? Andy? There was like significant
Oh,
concerns regarding
significant concerns regarding the storage of plutonium and proliferation.
Big proliferation concern. I think the public probably weren't too aware that this was kind of happening in the background, but there was a independent report and said you can't be storing hundreds of tons of separated plutonium without a long-term strategy. This is like it's a severely fraught situation that needs to be dealt with immediately, and that was nearly 30 years ago. Interestingly, between these two dates, something quite significant happened that I've not seen really explicitly referenced in too many documents, but obviously 9/11 happened between this. I do know that gave the nuclear industry a massive kick up the arse because it suddenly became like a new era of potential, I don't say the word, not an accident, but I think things can happen outside of normal warfare. I do know that I don't know if it was Thorpe or I went to one nuclear site at some point where they said they used to have a live feed of the vitrification rig and you could watch.
That was
the Stellarfield Visitor Centre.
Yeah, so you
used
could
to have a
watch
live feed
vitrification live just on a webcam, and that was turned off on
The day-
9/12.
Yeah, I thought it was the day after 7/7. They said, or maybe that was when they shut down the whole visitor centre. Yeah. Okay. Yeah.
But that changed a lot of things because it became a realistic possibility that you've got hundreds of tons of plutonium in a building that's very easy to find on a map at a site that's infamous as it is. You're in uncharted territory now. Updated recommendations in 2008, which basically said the same thing, like you've still not done anything, it's been 10 years, something needs to happen. So I imagine in response to that, the NDA published this document, which is called the Credible Options Framework. And this evaluated basically several high-level management routes that could be used to take hundreds of tons of powder and place it into a form that's essentially somewhat irretrievable, a lot easier to handle, alleviates theft concerns, fire concerns, terrorism concerns, whatever it might be. This framework was basically updated in 2010, then again in 2014, then again in 2019, and then we're landed where we are in 2025. So what were these options? So very briefly, these documents are very interesting. Some of them are very long and go into very detailed technical analysis and economic analysis, and I won't claim to be an expert in all of it. But what you read these documents and you see there was kind of 4 options that have been considered to varying degrees. The first one was sale. Now you don't see much talk of sale in the later documents, but if you read the 2008 one, this one here, there was a piece in there basically saying, well, somebody could use this material, whether it's the French or the US or somebody that's an ally at least. There was saying, well, we could sell this material for MOX fabrication. So this was basically shit canned quite quickly. Ultimately, it doesn't satisfy the disposition criteria, which is to place it beyond reach. If you give it to somebody else, you're basically removing the ability to confirm that it is passively safe and beyond reach. Once it leaves UK soil, who knows what could happen to it, no matter where you're selling it. It would also require several hundred shipments of plutonium overseas, which obviously then initiates new transport assets required, probably quite an expensive process as well. Indefinite storage. So obviously there is a requirement for continued storage, and the UK has invested a lot of money in the SRP, which is Self-Field Product and Residue Store. Ultimately, this is the highest technological readiness level because we do it. Its TRL is 10 or whatever the highest is. So some people say, well, just keep it where it is and just continuously upkeep. Have people basically on the door with a machine gun at all times forever. This doesn't reduce the generational burden. It doesn't alleviate the issues with degradation. So, although this is the baseline management strategy until a decision is made, obviously now it's being made, this isn't a feasible long-term solution. Then it comes on to the real contenders here. So, this is probably a conversation that we could spend all day talking about as to whether this was the right decision. Reusing it compared to disposing of it. So, there's the option to convert plutonium into MOX fuel, mixed oxide fuel, about 10 weight percent, and then this could be burned in some of the existing reactors that we have, or potentially new reactors. The UK's got a poor track record in in MOX manufacture. Even if we were to convert all this material to MOX, it would be quite an expensive process, so we'd have to build a plant. We'll have to build a plant either way. There's no demonstrated market appetite, so if you make this MOX fuel, there's no guarantee, and you can't make vendors buy it, right? You can't turn around to ADF and say you have to buy this MOX fuel. They could just say we don't want to. And importantly, it doesn't account for the non-usable material. So regardless, you'd still have to immobilise some of it anyway. So this kind of brings us on to what was known for a while, and Neil did a lot of work in this area, as what's called a dual track strategy, wherein you develop an immobilisation option in the background, and then if the decision and the policy changes, which it did, then you've already got that immobilisation option in your back pocket to pull out. And that brings us to where we are now. So immobilisation, in theory, is suitable for the entire inventory. It would be required for at least some portion. It converts the material into a passively safe waste form. 2025, great news for us. This needs a lot more underpinning R&D. The UK has now committed to this fully. There was a big investment of £154 million recently from the NDA's pocket to Sellafield to basically kickstart this process. Okay, so there's been several pieces of work at Sheffield. I won't spend too long on this, that have absolutely supported this policy decision. So it's very difficult to find, at least as far as I'm aware, there's no publicly available data that fully documents the information that was given from the NDA to the government to support its decision. What we do know is the NDA relied heavily on immobilisation trials that were done largely here at Sheffield. So one of these was the plutonium immobilisation programme, commonly known here as IKE. This designed and fabricated over 100 different con-like compositions with uranium and cerium by HIP and cold press and sintering, and commissioned basically the radiological facility we have here as part of that, and contributed basically substantially to understanding how HIP could be used to immobilise fluid at scale. And there was a lot of durability testing done on that as well. What kind of followed on from that was a project with NWS that has been fraught with controversy, as it seems. That's a story for the pub. But basically this was a follow-on project. Long-term evolution of candidate plutonium waste forms. So at this point, we established the Conlines feasible waste form. Pyrochlores are closely related to ceramic system, and then we have this so-called disposal MOX system that we'll come on to. But this established that a semi-dynamic ASTM C1308 dissolution method is arguably the best way, if not the most labour-intensive way, for us to be probing the release of uranium and eventually plutonium from these test samples. It also established baseline leaching behaviour of all three systems, all synthesised under standard, well-developed processing conditions, and also understood or seeked to understand the comparative radiation behaviour of each system as well. Over the years, this has led to various tranches of further funding. I show this slide when I'm trying to get people to give us more money, but I'll come on to plutonium-242 handling right at the end. As part of this, we've been very fortunate to have captured a big piece of funding in the plutonium ceramics hub. So the NDA, alongside recognising there needs to be technological development, there needs to be skills generation. This process will take decades and decades. I might not be around when the first portions of the stockpile are immobilised. I think I will be, but I like to drink and smoke, so we'll see. I might be well gone by then. But you're talking 50 years in the future by the time we're really in a position to start immobilising, no matter what waste form's chosen. So there needs to be a pipeline of skills. We need skilled researchers, PDRAs, etc. So with that, the NDA put out an open tender for a $5 million award for 20 PhDs, all focused directly on plutonium disposition, and 2 5-year PDRA appointments. And fortunately, with Rob Harrison at the University of Manchester, we were able to capture that. And our first 2 students are sat in the middle row there. What's the point of the Plut Hub? I bang on about it a lot. People and skills, understanding manufacturing routes, developing characterisation routes, and understanding material performance. They're the 4 things that really this investment is set out to do. I'm not going to spend too long on that. Fortunately, we are supported by several really strong letters of support for this. So first off, the European Synchrotron Radiation Facility contributed around $1 million in synchrotron access time, which we were overwhelmed with. This was very generous. This will allow us to measure cerium, uranium, and plutonium-bearing materials at the M4 edge on the Rovell beam line. This also mitigates the planned diamond shutdown in 2027, which is, I think the goalposts keep shifting for that, but diamond will go dark for a while. This kind of helps us alleviate that. Here's an example of some work that's been done looking at the uranium M4 edge in disposal MOX materials. And Lucidian and the Amric Centre. So for those who aren't familiar, Lucidian are, I don't know if they're classed as an SME, they're quite a big company, but they have the Amric Centre, which is the Applied Materials Research, Innovation and Commercialisation Centre, which is in Stirn, near Stoke-on-Trent. A large suite of powder processing kit, forming, sintering, large-scale HIP, multi-pellet furnaces, flash sintering. They're basically a translational company. You take them a process that you want to scale up from grams to kilograms, and they'll basically help you do that. And they're providing dedicated, basically ring-fence funding for training, training students, facilities time, etc. So the idea was hopefully we can take some of these small-scale ceramics we've made here at Sheffield and make them on, 20, 30 league scale in their hip. Okay, so what is Plut immobilisation? So Aidan gave a really nice talk earlier on zirconite, mentioned this material Synrock. Synrock was developed in the 70s as an alternative to vitrifying polysulfate glass. These very clever dudes were studying minerals, and they were like, well, these minerals are very old, they often contain actinides, they're thermodynamically stable, they've been underground, exposed to natural weathering processes, microbes, whatever it is, for sometimes billions of years. This is your best waste form. So with that, a selection were chosen. So hollandites, perovskites, zirconolites, and rutile are basically the most common ones of these minerals. And you can basically tailor the relative proportions of these phases to mop up whatever your waste is. So there were different flavours of Synrock for different wastes. Synrock C was developed as a standard reprocessing waste form, should I say, where the hollandite takes up the large cations, that are things like divalent and monovalent, so cesium, rubidium, nickel, whatever it might be. Zirconolite serves your host phase for actinides, and the lanthanides as well, the long-lived lanthanides. And then perovskites there for lanthanides, actinides, and things like sodium. But as the waste form sort of philosophy has evolved, people thought, well, if zirconolite's your single phase, so zirconolite's your actinide phase, this should just be a single phase ceramic waste form to immobilise basically a fairly pure stream plutonium. So with that, I've done a lot of work trying to basically turn this zirconolite sample, or this zirconolite system, into something that's reproducibly a single phase material that doesn't really vary in its feedstock too much, can accommodate a few weight percent here or there of other things. So we've done things like trialing different processing conditions, pellet sizes, sintering times, temperatures, etc. Charge balances. So Aidan mentioned earlier we're looking at iron. This has kind of moved away from the original thought piece, which was aluminium. And the reason the aluminium was first chosen is that all the initial Synrock phases contained aluminium because a lot of the natural zirconolites formed with aluminium. So obviously it's quite rich in the first, as is iron as well, obviously. But for whatever reason, something maybe I'm not too sure of, the natural zirconolites tend to contain aluminium. Done a lot of work trying to understand the incorporation of uranium and cerium in zirconolite. We understand that you can dope uranium and cerium, all surrogates, onto the zirconium site in an isovalent substitution. And this produces the formation of different polytypes. So you can see here in the EPMA image at the top, got zirconium, titanium, and uranium. The colour maps here basically show where uranium is concentrated, and what we find is that uranium tends to preferentially concentrate in a zirconolite 4M phase, which is, in my opinion, not a bad thing. If we try and demonstrate a waste form to the regulators, they tend to want single phase materials because ultimately they're more predictable. Solid solution limit's about 15%. X-ray absorption spectroscopy analysis has been done across many different solid solutions. Largely what we find is that cerium tends to reduce regardless of what conditions we process it under. The only thing we've not tried is pure oxygen. However, I don't think that's feasible, not really. And even if you could synthesize pure cerium-4 in only pure oxygen, there are additional constraints with that. Uranium tends to form mixed U4-5 regardless, unless it's under fully reducing conditions. Again, this is just a very brief snapshot of a lot of spectroscopy data. If you want more information, Aidan's the man to speak to there. HIP. So HIP is the preferred thermal treatment route. And why is that? It's a batch-wise process. You've got high accountability, you're producing a discrete number of canisters. It's not like vitrification where you've got a continuous process. You know, if you went up to however many hundreds or thousands of high-level waste containers there are, you can only probably, I imagine, estimate what the rough amount of waste is in each one. You might have slight batch-to-batch variation, whereas this you've got a bit more of a control process because you're just making each canister kind of on its own. So simultaneous application of isostatic heat and pressure, realistically 1300 degrees and 200 megapascals is kind of upper limits of what we envisage. And in Sheffield we can produce UO2, obviously loaded waste canisters, and thorium oxide loaded waste canisters. So this is what a realistic waste form would look like, about 18% UO2. You've got high density matrix on the right hand side, and then as Aidan showed, you've got this sort of interface region. And the chemistry of this interface region isn't too well understood. What you really don't want to do is form something that contains plutonium, because your groundwater is going to penetrate the can from this side. The first thing it's going to encounter is this interface region. So you don't want to preferentially bias the leaching rate by having a wall of plutonium just as it comes in. Durability of hexaconolite is something that we've looked at before. I won't spend too much time on this. You need to basically minimise perovskite content at all times. We've established with fairly high degree of confidence that if you have plutonium containing perovskite, that will act as an increased leaching mechanism. Essentially, it will come out a lot easier, and we can basically characterise that by looking for rutile precipitation on the surface, and we do see that. A bit of work on the americium then, I'm not going to spend too much time here. Some work we did a few years ago looking at, okay, if you take dysprosium as an americium surrogate, can you co-modulise that into conolite? And we just made a full cell solution, and what we found is that we get progressive transformation from conolite 2M, which is the sort of parent structure, through to this 4M phase, which is a superstructure, and then onto pyrochlore. And through some nice systematic XAFS analysis, we basically demonstrated that you've got a dysprosium environment that's more consistent with a mixed 8 and 7-fold in the lower concentration samples, all the way through to an average 8-fold coordination in the pyrochlore. There's some really nice TM here that we did in collaboration with the Sorby Centre, and what we see is that we get this nice sort of systematic repeating of these unit cells. If I zoom in here, you've got sort of lattice fringes that are really quite resolvable, and you can measure these directly. And these basically, this corresponds to basically doubling the unit cell form to conolite 2M to conolite 4M, and you can see that reflected in the diffraction as well. Neutron absorbing additives. So this is an important one. So if you're putting plutonium under the ground, you need to basically ensure that the risk of a post-closure criticality event is unlikely, and that the consequences of such an event would be minimised. And basically the easiest way to do that is to do it in a neutron poison. So there are a bunch of proposed additives: gadolinium-3, hafnium-4, indium-3, boron, samarium, and things like erbium as well. Basically something that's got high thermal neutron absorption cross-section. So we did some work looking at indium substitution, because nobody's ever really fabricated indium containing pyrochlore into conolite phases. There are some weird examples of indium phases for other applications, but we were starting from scratch basically. And what we found is that unlike the rare earths surrogates, so lanthanum and lanthanide, that have got a 3+ charge, I thought they behave very similarly. They didn't. Indium substitutes for titanium. We inferred that through some careful analysis of this spectroscopy data. What we then found is we can self-charge balance indium on the titanium side, and we can accommodate both U4 and U5 in solid solution. So that was a nice systematic study. Some work that's been done, we've also looked at hafnium. Hafnium is a bit more of a straightforward closed book. Hafnium and zirconium have got very similar solid solution behaviour in ceramic phases. So you can basically directly substitute them. But it's nice to be sure. So some hafnium L3 edge XAFS was performed, and this confirmed that we get an average coordination of 7, which is consistent with zirconium in zirconium. So that was nice and leaching behaviour. So I've only put one slide on this one because it would be an injustice to former colleagues Laura and Amber, who have done an insane amount of work on this, and Sarah Pepper as well, who analysed all the ASIP data. There were some very large, very prolonged durability tests that have happened, but the two most important bits of data are here. So on the left-hand side, what we have is leaching rates, so grams per metre squared against time. RWM1, so this is a zirconolite sample. RWM4 is a pyrochlore sample with the same amount of uranium, and DMOX is a surrogate disposal MOX system. So I'll come on to DMOX in a minute. This is the uranium leaching rates. So take-home messages: uranium pisses out of DMOX a lot easier than it does for the titanate waste forms, and this zirconolite had consistently low leaching across the time. Within the zirconolite space, we have different amounts of uranium, different charge balancing species. So aluminium, iron, and magnesium. Take-home message: the iron sample is leached the least. So these two pieces of information together tell you that your waste form should ideally target uranium, iron, zirconolite. What is dispersal MOX? So dispersal MOX is an idea that's been around probably since the late 90s, but it basically says, well, you could make basically low quality fuel that you could use an established design for. You can basically buy a MOX plant, or design for a MOX plant based on, for example, the French process, so the MIMAS process, which is where you take uranium and plutonium, you mix them together, ball mill them, form a master blend, add in some UO2, press it into pellets, and make fuel pellets. All the scrap that falls off just gets recycled back in. So you could basically buy this process, you could build it, and all you're doing there is then at this first stage where you've got uranium and plutonium, you just add in some gadolinium or some hafnium or whatever it might be as your neutron poison. So we've basically mocked up a similar lab scale process, and we've demonstrated that we can form single phase fluoride product. And then a lot of work has been done. I won't spend too long on this. Latham is the man to ask about disposal MOX. A lot of work's been done here. But how we understand the charge compensation mechanism to be is no U5, which is interesting because even if you have a little bit of something like chromium in the same system, you do tend to get quite a lot of U5 forming. Whereas the Hereford measurements combined with Raman data tell us that actually oxygen vacancies are what are accounting for the gadolinium in solid solution. And then we've done a lot of EPMA on the products as well, comparing wet and dry routes. I'm going to skip over this a little bit. We've done a lot of radiation damage work. In situ TEM work at University of Huddersfield. This can kind of tell us about the amorphization behaviour. So we take fibromellar, zirconolite, we do electron diffraction before, and then we irradiate it in situ, and we get full amorphization. Not to be, this was expected. About 2.7 times 10 to the 14 iron per centimetre squared when looking at 600 kVs energy. You can basically do these experiments at different temperatures, and you can build something that looks like this. So you get like an amorphization curve as a function of temperature. This is important because the waste packages will be at temperature, so it's important to know if you're in this kind of thermal recrystallization region or not. Bulk ion irradiation has been done at the University of Surrey and also at DCF. A lot of spectroscopy work here. Aidan and Latham have done all this, as well as Lee Townsend. Basically looking at ion coordination, and what we see, interesting result. It's basically a one-off result, and we get to do more work on this. What we see is that ion changes coordination with irradiation rather than titanium, and that's important because we don't really know why that's happening, and there's a lot more to be unpicked there. A little bit more on in situ ion radiation. We've done a lot of work on transitions from pyrochlores to defect fluorides, and again, you can build these kind of fluence maps. And here we've got tin content against amorphization fluence. So this is all Latham's work. Okay, so what's next? So very recently, the plutonium glove box was switched on, which was a momentous day.
The gloves are the wrong way there, though. Now the box pulls in rather than pushing out.
At least they're wrong. So the next steps are to fabricate plutonium-242 containers of conlines here in Sheffield, and a 0.5-year PDRA, which we've done. So the first thing is going to be leading training and supervision of plutonium ceramic hub students. We have plans to try and get some of the plutonium-containing cinema to NNL into the SEM, and then we're getting basically progressively more from realistic to like pipe dreams here. Take the plutonium combines to ESRF, forage analysis, that'd be nice. Eventually I'll get an issue to let's see, and then my Nobel Prize is going to be in the purse probably for the next 60 years, but you never know, you might get there eventually. Huge list of acknowledgements. This is a huge team effort. Latham, in Alex, and Ishi, not least, for being excellent PhD students, and Ishi for being the longest standing PhD student I think this group's ever had, for various reasons. Sarah for ICP-MS analysis, which has been hugely consistent and reliable. Stuart, Inam, and Christina for EPM-ATM and Hereford analysis. A whole list of former PhD students and postdocs for many years of science analysis, and now a sort of shared trauma bond from the last sort of 3 or 4 years. Neil, Claire, Russell, Claire, Carl, and Grant for just continued academic support. And last but not least, the man of the hour, Martin Stendock-Stennett, for being an absolute gem. Favourite quote of all time, don't let the motherfuckers get you down. That's going to go on my gravestone, I think. But yeah, the group would cease to function without you.
Where did you get that picture?
I'm not telling you where I got the picture from. The work getting the plutonium lab, no one other than Mark can take credit for. It's all him. So the next 10 years of work are a testament to you. So thank you most of all. And with that, I'll stop. Cheers.
Thank you. That's very, yeah. I want to know where you got that picture.
You can't really reveal my sources.
I know where that one came from. But
Yeah, that one came from.
There's a backlog of historic photos of you, Martin, scattered around the Google Drive, which have been slowly revealing themselves.
Any questions?
Quick question. I know the hafnium follows zirconium around. If you try and analyse the zirconium sample, there's only a bit of hafnium there.
Yeah.
Presume your hafnium is deliberately added though as a neutron poison.
Yeah. So there is some thought there as to, well, could you just buy a really impure zirconium source, and then what you'll get is a bunch of hafnium for free. And I've thought about how to kind of go about this, because on a supply chain scale, cost will become a big factor when buying these chemicals in bulk. If the NDA's got to purchase hundreds of tons of zirconium, for example, if they can buy an impure grade that's got hafnium in there, it's probably not a bad thing.
just take that slide down because it's giving me a complex.
John?
You mentioned about the chlorine kind of being in the plutonium.
Yeah.
What sort of, is it going to be an issue in terms of the waste form because it's obviously so small? And B, if it is, what do you reckon that might be?
So NNL have just published, in the last few weeks, have just published their first reports on immobilising plutonium loaded with chlorine. I'm yet to fully digest the report. I'm not properly sat down and read it cover to cover, but from what the conversation I've had with Dan Lemon is, it doesn't seem to be that much of an issue for the comlines. But I think they're doing a lot more work on that. So I don't really know the answer.
Could you just go back to your slide where you were talking about the ion changing coordination upon irradiation and not the titanium?
Yes.
And I haven't. Good. It's unpublished. I was going to say I haven't read that one. Are you seeing any changes in oxidation state that accompany these changes in coordination, or is it purely it stays in one oxidation state and then it changes coordination?
So on up here, so on this basically this side of the, it's quite a confusing figure. The pristine zirconites around here, so all the ion standards we've got, the iron 3 tends to be in this centroid position. The iron 2 samples, the standard reference materials are all kind of down here. So before and after. So if we're assuming iron 2 to iron 3 to basically be linear along this axis, there might be a bit of a change, but it doesn't look like much. So what we'd really like to do is some moss batter, or something that's a bit more sensitive perhaps to understanding oxidation.
I would say on the basis of that data, certainly there's not strong evidence for iron 2+ formation. So.
Okay. Yeah, I mean, we can help with moss batter if you know, if that would be useful. I guess my only question would be, you based this on fitting of the pre-edge peak to iron K edge zones, right?
Yep.
You've got a complex underlying edge function, and then you've got to fit essentially a number of Gaussians, which may or may not be Gaussian functions. So I'd suggest there's maybe a little bit of uncertainty there. It would feel sensible to me if you do see some oxidation change, however modest, and it's a lot easier to reduce iron than it is titanium, which would be consistent with the fact that the titanium isn't doing much. Just some thinking out loud, really.
Absolutely, there's definitely more to be done here. A lot more difficulty as we've got such thin irradiation regions.
Would you like to do EPR while you're at it?
If you can take the samples, some they are active. That's the downside.
The other issue that you've got there with it as well is that we're talking that in terms of the size of the sample, the layer that's irradiated is about 0.01% the thickness of the overall monolith. So a lot of all the data that was collected here, that was collected in grazing incidents, we were lucky to be able to get much further than the actual edge. That's like meaningful data. So like the uranium L3 edge was able to be collected on the uranium concentrate sample, so the DMOX, but for the zirconolite, I don't know about Ed, I know that you have like a pretty rough time trying to get anything meaningful out past that.
Yeah, I think you're right that it's more complex than a simple change in coordination. But yeah, probing that is very difficult because just purely because of the nature of the sample.
And the other thing that's compounded all of this is that you're looking at zirconolite, which is a deviation from the pyrochlore structure, which is then a deviation from the fluoride structure. And what we've been seeing from a lot of the Raman data that's come out of this is that you're essentially reforming some of those substructures from those prior derivative minerals. So the issue that you've got there is you have one system that can continuously transform between two other mineral structures, each one of them that can accept different coordination states and oxidation states. And we've seen like big changes in uranium oxidation state. We've seen combinations of amorphization and then potentially some extra peaks that have cropped up. When this was first put together as a study, I think it's highlighted that you have to kind of add one thing at a time to see what's going on. That's where a lot of like Alex HR's work is coming into it, is taking that more stepwise approach at seeing how the irradiation process affects those different sites. Because there's a lot to it, and also that lack of change in the titanium coordination environment goes against a lot of the conventional understanding of these ceramics anyway. So we're deviating from everything basically very quickly.
Glass is easy by comparison.
Right, in the interest of time,
Thanks,
we'll
Latham.
pass on to our last talk, which is by Martin, I imagine, on some radiation damage.
I think I'm going to shed some additional light on this now.
Okay.
And then Martin is the only thing that's standing between us and the pub. So
I will be brief.
well, I mean, we've got a pub up to 5, so there's no rush. Where's your talk?
It's on Google tonight.
That is complex.
We can chat if you're interested, but there's all kinds of studies. Loads of really interesting.
Do you want to sign it?
I sign it.